So, we talked about bound currents in the material, magnetized material. If a material is magnetized, that means it has magnetic dipole moment per unit volume in whatever way this magnetization is produced. Then you have these two equations, curl of M is JB, this is bound volume current density, so if the magnetization in the given material is non-uniform and non-uniform in such a way that the curl of M comes out to be non-zero, then in the interior of this material also you will have some currents, and these currents are bound currents, remember, and bound currents are the currents because of the atomic electrons, motion of atomic electrons in the vicinity of the atom. The electron will not go through long circuits or like that, that is for free currents. But then these alignment of these atomic currents will be such that it will give a current in the volume wherever this curl is not zero. And the other equation is this M cross n cap, this is KB, this is bound surface current density. So, that we derived, and most of the time we talk of uniformly magnetized material, then in the volume there are no currents, but on the surface, on the periphery, on the surface, anywhere on the surface you will have this M cross n cap, this much of bound surface current density will be produced. So, that means on the surface a current will be there. This is also bound, it is also because of tiny electron movements in their in the vicinity of their atoms only, but as a whole it gives you a current on the surface. So, these two are the basic equations, and you can obtain the magnetic field of a magnetized material. If you have a magnetized material and the magnetization is known, then you can use this equation to write what is the current density inside, use this equation to write what is the current density on the surface, and then from the currents, from these currents you can write the magnetic field using the usual techniques, Bat-Savart law or Ampere's law or vector potential, from their curl of A is B, whatever suits. So, this is the procedure. Now, when you do the magnetization, most of the time you apply a magnetic field, external applied magnetic field, you apply a magnetic field B, external or applied, and put the material here in the magnetic field, and this magnetic field magnetizes the material. But once the magnetization is obtained, then this magnetization also creates magnetic field that we discussed just now, that you will have currents, and that those currents will also produce a magnetic field. So, this applied field is perhaps because of some free current, some current solenoid or something, or this may also be because of a magnet, but then you have a magnetic field because of this magnetization also, and therefore, your magnetic field is your applied magnetic field and plus the magnetic field because of this magnetization. So, it will change. If you put the material here, the magnetic field everywhere will change, because this will also produce its own magnetization, and the two will get mixed up and the magnetic field will be this. Now, it is useful to define a vector H. It is useful to define a vector H vector. I will just call it H vector. Its name is not yet very standard. People call it magnetizing field. The several names are in use. So, we will call it just H vector to avoid any confusion. That H symbol is universally used, and this H is defined as B over mu naught and minus m. B over mu naught and minus m, this is the definition. So, we construct this vector, we construct this vector. B is the magnetic field, it is a physical quantity. This magnetic field is that exerts force on the charged particles in motion, or on current loops it exerts torques and many things. It carries energy in electromagnetic waves, this magnetic field carries energy. So, this is a physical entity. Magnetization is a physical entity. Once your material is magnetized, you have a dipole moment and per unit volume will be this, but this is our mathematical construction and we construct this H vector. It is useful, that is why we construct it. Okay. Now, in many of the cases it so happens that when you put the material in your applied magnetic field, then this material changes magnetic field B, but this material does not change this H. H is independent of this bound current thing that appears in this material. So, let me take an example. Let us suppose we have a solenoid, a long solenoid. First start with a long solenoid. I, current I, and every turn the current is I, n is the number of turns per unit length as usual, and outside B outside is 0, outside there is no material, inside also there is no material, material is only in the wires. So, B outside solenoid is 0, B inside solenoid is mu times n times mu naught times n times I. So, B outside is 0, m outside is 0. Here there is no m. Why? There is no material. There is no material here. So, no question of dipole moment, magnetic dipole moment, etc. So, m is 0. Inside also there is no material. We start with this just a solenoid. So, B inside is mu naught Ni k cap. If I take this as the z direction, this as the z along the axis. So, B inside is this and m inside is again 0, and therefore, you write H outside which is B, which is 0, divided by mu naught minus m, m is also 0. So, H outside is 0, and H inside is again B over mu naught. So, B over mu naught, that will be N I k cap, and minus m, this m is 0, inside 0. So, H inside is this and H outside is this. Now, let us fill this solenoid with a rod, So, we put a rod here. You can put a rod of some other radius also, or the entire volume can also be filled with the rod. This is also a long rod. And let us say this radius is R1, this radius is R1 and this radius is R2. The rod gets magnetized, and assume that the magnetization is uniform, because the field which was existing here mu naught Nik, that is also uniform everywhere. So, whatever happens to this part of the rod, same thing should happen this part of the rod, and so on. So, this rod gets a magnetization capital M, which is uniform, which is constant everywhere. Now, what happens to B outside with the rod? So, just outside, that means outside the solenoid. So, R is greater than R2 here, outside the solenoid. Now, this magnetized rod, for all our calculations, it gives you a surface current. The curl will be 0, uniform magnetization curl will be 0. M cross n cap will be the surface current, and for this M is m k cap. And what is n cap? What is n cap? You have this rod, and then you are on the surface, and you are asking the unit vector along the normal direction. So, that is our s direction, cylindrical coordinates, and therefore, m cross n cap will be m k cross s cap, and that is phi cap. So, you have surface current. And per unit length, the current is that m. This is the current density. This is Kb. So, this is Kb. This is our current density Kb on the surface of the rod, and therefore, per unit length of the rod, if you see how much is the current, that per unit length current is this m. Just like per unit length, the current here in the solenoid is small n times I. This is the current going through per unit length. There it is this. So, because of this, there will be a magnetic field. So, our magnetic field here is okay. Here it is 0, because this is again a solenoid. So, this magnetic field outside is 0. M outside is 0, and therefore, H outside is 0. Good. Obvious. So, this is for R greater than R2. Now, your R is somewhere, let us say here, let us say it is here. This is our point. So, R is now less than R2, but greater than R1, outside the rod, but inside the solenoid. Once again here for this B, what is B? B is due to the solenoid. For this it is an internal point, but due to the rod it is outside 0. This rod itself is a similar solenoid because of the same kind of current phi cap direction, and m is the current per unit length. So, this m is taking the role of n into I. So, outside this, the magnetic field due to this rod is 0, and for the solenoid, the magnetic field due to the solenoid is once again this. So, B is mu naught n I k cap. There is no magnetization. There is still no magnetization, no material here, and therefore, if you calculate H, that H will be n I k cap. Here also it was n I k cap inside the solenoid. Here also it is n I k cap, but we have taken this region. What happens inside the rod? Because here you will get to magnetic field from this surface current also. You will have the magnetic field due to the solenoid, and you will also have magnetic field due to this rod, which has bound surface current in the same fashion. So, what happens here? So, for R less than R1 inside the rod, what happens? Here you have magnetic field due to the solenoid, and that will be mu naught n I k cap, right. This is a point inside the solenoid. So, the magnetic field is B is mu naught n I k cap, and then you also have current in the same direction, in the same sense, and that surface current is K. So, B, because of the rod, will be mu naught times K, which is mu naught times n, m, mu naught times m. because here the surface current density is K, per unit length it is K, here per unit length was N into I, and they are circulating in the same directions. So, you will have magnetic field because of this rod, magnetization of rod, because of this bound surface current in the z direction, and then the magnitude will be given by this. So, B itself is this plus this mu naught times N I k cap, and then plus mu naught times M k cap. Because of this magnetized rod, the magnetic field has changed, increased. All right, good. What is H? What is H? H is B over mu naught and minus M. And now you are inside the material. Now you have inside the rod. Here there is a magnetization, and that is M. So, B over mu naught, here is B, here is B. B over mu naught is N I k cap and plus M k cap, and minus this magnetization, and magnetization here is capital M. In what direction is the magnetization? It is in k cap direction. So, minus M k cap, and this cancels, and it is N I k cap. Okay, N I k cap here, N I k cap here, and N I k cap here. So, this was the H inside the whole solenoid here, everywhere. Before putting the rod, this was the case, inside was this and outside was this. And after putting the rod, what happens? Inside is still the same, we have taken both the cases. Between R1 and R2, that means outside the rod but inside the solenoid, and also R is less than this rod radius and smaller than solenoid radius. So, everywhere, whether you take inside the rod, which is this case, whether you take outside the rod but inside the solenoid, that is our this case, or whether you take outside the solenoid, the H field before the rod was put and H field after the rod was put is same, and it is Ni is the external, that the solenoid that is Ni k cap is just the H field of the solenoid. So, this magnetization, this magnetized rod is not producing H field, it is only the solenoid that is producing this thing. So, that is how H is defined, and that is the benefit of H in some cases at least. But this is not always the case. This is not always the case. If I take another example, let us again take a long solenoid. Let us take this solenoid, again that small n and I cap will be there, I will be there, each turn will carry a current I, and n will be the number of turns per unit length, tightly wound, do not go by these separations, tightly wound solenoid. And inside this solenoid, let me make it a bigger solenoid so that the discussion is easy. Inside this we have a disc. Suppose we put a disc here. So, this is a disc, this is the top surface and this is the side surface. This is, let us say, circular disc, this is a circular disc, and the radius of this circular disc is, let us say, small a, and radius of this is some capital R, let us call it capital R. Okay, and it is magnetized. Once the solenoid current is there, magnetic field is there, that magnetizes this, and this magnetization in this is mk cap, just like our rod. Only thing, the rod is now not of a large length, the height is only this much, and this is, let us say, h. This thickness of the disc is, let us say, h. Now, before the disc, without disc, let us say without disc, when the disc was not there, h was Nik cap, just the solenoid, we have calculated it just now. Because of the solenoid alone, h is Nik cap. Now this rod disc is there, and the disc is magnetized, uniformly magnetized, and therefore curl of m is still 0, no bound volume current density. But then you have this m cross n cap, and that will be in phi cap direction, and the magnitude will be m. So there will be a current density here, and the current will flow like this. The current will flow like this on this periphery, the curved boundary of this thing. No surface current density on this surface, because m and n cap will be in the same direction, and this cross product will be 0. So no surface current density on the top surface, no surface current density on the bottom surface, but on the curved surface, yes, there is a current density, and that current density will be Kb. This will be m phi cap. We just discussed these things in our previous examples. Now let us write what is the magnetic field here at a distance z from this disc. This disc is short, thickness is small, so we can take the distance from anywhere, center of the disc, let us say, and then z is large as compared to h. So this is just like a current loop. This is just like a current loop. How much is the current? How much is the current on the curved surface? This current will be I1. This current will be m times h. M is the current density, surface current density. It's going like this, and perpendicular to this is the line which it is crossing, and that line has length h, and therefore the current will be this current density m times this h, that is the current. So now you have a circular current, and of the radius of that circle is a, and from the center at a distance z on the axis, the magnetic field. I am asking for the magnetic field. So magnetic field, B field, due to the disc, let us first write that B1, due to this. And if you remember the equation for magnetic field at the axis of, at a point on the axis of the loop at a distance z, that was B mu naught times current is I1, and then a square, the radius of the disc square, and divided by 2 times a square plus z square 3 by 2. Okay, we had derived it when we were discussing Biot-Savart law. So this is B1, and I1 is of course m times h. So this is mu naught m times h times a square divided by 2 a square plus z square 3 by 2. So that is the magnetic field here because of the disc. And what is the magnetic field here because of the solenoid? That is mu naught times n times I. So the net field, net B field will be, B will be mu naught n I k cap. this I is this I. So, mu naught n I k cap, this is because of the solenoid, plus mu naught m h a square divided by 2 times a square plus z square and 3 by 2. This is B. Here, what is H here? H is B over mu naught minus m. So, first divide mu naught. So, you get n I k cap plus m h a square divided by 2 a square plus z square 3 by 2. So, that is B divided by mu naught k cap and minus m k cap. Minus m, this m vector is magnetization vector is m in k cap direction. Now, you can say that before putting the disk, without the disk, H was n I k cap, and now after putting the disk, it is n I k cap and plus this quantity, and this is not 0. This is not 0. So, H has changed. So, in some of the cases, the H is only decided by the field that you have applied from outside, and the magnetized material that is creating a magnetic field is contributing to the magnetic field, but not to the H field. And in some cases it is contributing to the H field also. So, what are those conditions, when we can have that kind of situation, when we have this kind of situations, those things we will discuss in our next lecture.